Example here. So we've got an initial value problem, a relationship between x, y and its derivatives, and y1 is equal to 0. So all I want to do is use Euler's method with a step size of 0.2 to estimate what's going on at 1.6, where y of x is the solution. So you can use a table, but it's not strictly necessary, but I have one down here that we can refer to in a minute. First of all, this is not in the correct form because you need the derivative in terms of x and y. So I need to add x to both sides and take away x by y from both sides. So I end up with dy dx, or y dashed of x, is equal to, so add the x to both sides, take away the xy. Now I'm going to write this as x just times y, because this y of x just means y. It doesn't mean y times x. Well, xy means, yeah, okay. Now I'm going to write down the kind of form that we'll use for Euler's method, which will be that the next y value is equal to the previous y value plus the step size times the previous slope. So I'm not putting in the big F of xy business. So let's start using Euler's method here. And we'll think about what we're doing as well. So I'll put in the approximating bit. So we've got x equal to 1, and we're trying to get to 1.6 in steps of 0.2. So we're going to jump from 1 to 1.2. So we're interested in the y value at 1.2, which is approximated by what we call y1. Now y1 is equal to the previous y value. So looking down here, we're trying to find out what's going on at 1.2. The previous y value is 0. Plus the step size here, the difference between the x values is 0.2, times the slope at the previous point. Now our slope depends on x and y, but our previous x is 1 and our previous y is 0. So if we multiply here, we will have the previous x was 1 minus the previous x is 1 times previous y is 0. And this is equal to 0, this is 0, so you get 0.2 times 1, which is 0.2. And that goes in the table here. So this is our approximation to the y value at x equal to 1.2. Now we go again. So the y value at the next point is approximately what we call y2, which is the previous y value, which is 0.2, plus the step size, which is 0.2 for the whole problem, times the slope at the previous point. The slope is x minus x times y, and the previous x and y values are 1.2 for x and 0.2 for y. So x minus xy, the previous x is 1.2, minus previous x is 1.2 times the previous y is 0.2. So just to make a little note here, just in case we're not clear of what's going on. So this is the previous y value. This is the step size. And then times the previous slope. The slope is x minus xy. So this must be previous x minus previous x times previous y. x1 is 1.2, y1 is 0.2. And using the calculator, and to be honest, I'm not actually using the calculator, I'm just looking at the table down below, this is equal to 0.392. And so now we're at what's going on at 1.4, and the question was to find out what's going on at 1.6. So we do one more. So get the y value at 1.6 is approximated by y3, which is, now this time I'll do the blue formula first. So it's the previous y value plus the step size times the previous slope. And the previous slope is x minus xy, so x2 minus x2 y2. So you get the previous y is 0.392 plus the step size all day long is 0.2. The previous x to here is 1.4 minus 1.4 times the previous y value is 0.392. And this is equal to, and I'm fairly sure there's no rounding, this is the exact figure, 56224. Now, if you're doing this by hand, if you're going to go one further, you're probably going to have to start rounding this. Like if you get to, like it will event, like you're going to be multiplying this by 0.2, by 1.6 and 0.2. So you're going to add in 2 more decimal places. Eventually, you're probably going to have to round these. So not only you're going to have the error from Euler's method not being that accurate, you're also going to have the rounding errors. Okay. So question here, the exact solution is given by this jalopy, which we'd normally just write as 1 minus e to the power of 1 minus x squared over 2. Something interesting about that. Okay, find the percentage error. So the exact value is we put in 1.6 to this exact elementary solution. So I get y of 1.6 is equal to 1 minus e to the power of 1 minus 1.6 squared over 2. Now I'm going to round this to 5 significant figures. That's usually what I'm going to recommend here. So 1 minus e to the power of, now I've got this, 1 minus 1 point, I'm crap at a calculator, divided by 2. And I get to 5 significant figures, 0.54159. And it's probably good to match the precision. Yeah, okay. So the percentage error, remember the error is going to be the difference between the approximation and the true value over the true value. So the error, percentage error, let's just call this percentage error, is the error over the true value, which is y 1.6. So the error is the difference between the approximation and this. So that would be like y of 1.6 minus y of 3. Take absolute value just to make that positive, divided by y of 1.6. Now I'm just going to write up here, because I'm not going to write, I don't like writing out decimals. This is your y3. So here I get approximately, let's see what I get. 0.56. Now this is already an approximation because this is rounded here. Now I'm very like to make little mistakes in the calculator, so so this comes out to be 0. If I just do maybe 2 significant figures for a percentage, 0.38, which is approximately 4%. So we get a 4% error. Okay, so I think that's enough for you to go off and do your VBA lab.